Hey, Kinetic Mind 89 here once again. We're going to teach you some more physics. Today, we're talking about magnetic force on a current carrying conductor. Not that much different than my last video. We talked about the motion of a charged particle in a uniform magnetic field. We're still talking about a uniform magnetic field today, one that does not vary. And we're still talking about the motion of charged particles. We're just talking about a whole bunch on a wire, like a lot of charged particles moving through a wire. So not a lot different than what we had before. I'll start with some illustrations here. These X's and these blocks represent a magnetic force going inward towards a magnet. So imagine this being the south pole of a magnet and there being a north pole out here, and there's a magnetic force going in towards the board. So if you remember, and I've had this little cool device using the right hand rule. If you remember what happens, right here we have no current, which means we have no charged particles in motion. So no moving particles, charged particles, to be affected by the external magnetic force, because this is just a wire between the two poles of a magnet. That's what the straight line is here. And when we turn the current on over here, what we get is a current in the upward direction. So we're going to use our little cool thing here. Remember, we have magnetic field is B, velocity, this is the force of the magnetic field, and this is V. And we can use this to determine, or our right hand rule, to determine which way our force will act, our magnetic force will act. And remember that this is going to be exactly the same as a single particle, or a single charged particle. It's just going to be a collection of particles in a wire. The sum of force on the wire is the individual forces of the individual particles, charged particles moving through the wire. So really, we're just talking about a bunch of particles. Same thing as last time. Instead, there's a bunch of particles moving through a wire. So no big difference there. But let's get into this. Let's talk about what's going to happen. So again, our magnetic force is going inward in the board. So B is our magnetic force. So that's going inward. And our current is going up. So with our current going up, see this is our V. This is the velocity of, it's called the drift velocity when we're talking about current moving through a wire. It's called VD for these purposes. But our current's going up, so VD is going up. That's the flow of our electrons. B is going in, so our right hand rule, what do you say? Our force goes to the left. And that's what direction our wire is bending here. So, with the movement of the electrons, the velocity is in the up direction. The magnetic field is in toward the board. What do you know? Like I said, the force is going left. That's what's moving this wire left here, as opposed to no current in here, no motion of charged particles. So, even though there's a magnetic field, the wire is not being pushed because there's no charged particles moving. So again, just to re-emphasize, I've said this in the last video, magnetic field is the region surrounding a charged particle in motion. And these are independent magnetic fields. The actual current creates a magnetic field, but we're talking about the magnetic field created by the magnet. Now that is the external field, and the charged particles moving through the wire is what's being affected by that external field. And you'll go over here, look with me a little bit further left. This is our three basic equations for this topic, for magnetic force on a current carrying conductor. And when we talk about conductors, we're mainly just talking about wires. They could be any shape, really. These are the simple equations. It's just talking about straight wires of any uniform thickness, no varying thickness in the wires. This is for a wire of the same cross-sectional area or diameter. But we'll talk about a little bit more equations later that can deal with curved wires and wires of different shapes. But this is just for straight wires, like this one. The equations up here to the right we're talking about. Okay, so the magnetic force on a current carrying conductor is Q, which is, we've talked about that before, that's 1.6 times something. It's a given, it'll be given to you, it's a constant. Times VD, the velocity will also most likely be given you in the problem. Whichever one you're looking for, most of the others will be given. I can't say which it will or will not be, depending on your professor. VD is that drift velocity. That is your current. That's how fast these electrons are moving. Well, they could be protons, most likely electrons. How fast they're moving through this wire. So that's your VD. And then your B is your magnetic field. That's what your B is. What we've been talking about here is Bn, mean is going in the board. Your N is the number of electrons or number of charged particles, could be protons, within a given volume. So you may have a cubic inch of wire. You may have like 1,000 electrons per cubic inch. That's not a realistic number, but you would have something like that. That's what this N would represent. Your A is your cross-sectional area, which would simply be just how the area of your wire. Say if this is the wire right here, this circle, and that's a horrible circle. But this area all in here, if you look at the wire from the front of it, the thickness, that's what your A would be. And your L is the length of the wire. That's what L is. It's actually how long it is. And in simplifying this equation, we can go back to the definition of current. Our definition of current, I being current, is N, which is the number of charged particles per unit volume, which I just discussed. How many would be in that, how many could we fit in a certain area of wire, like an inch of wire? How many particles can we have in there? It'll be given to you as a problem most likely, or you'll have to solve for it. The other ones will be given to you. Then we have Q, that constant. Then we have VD, that velocity. And then we have A, cross-sectional area again. So this is the definition of current. So we can substitute some things and make this a lot easier. Our final equation ends up being the force of the magnetic force on a current carrying conductor is I current times L, which is the length of the wire or the conductor we're talking about, which is in vector form, and L is always in the direction of the current. If current's going up, L's in that direction. If current's going down, L's in that direction. But sometimes you'll just be asked for magnitude. Sometimes current is not relevant. But with that being said, the cross, so you have I current times L, which is the length of the conductor, crossed with, because it's a cross product, that's why I say cross. It's not multiplied by, it's a cross product, which we use our right-hand rule to determine the direction, as I showed you before, crossed with the magnetic field B. So this is how we determine the force. This is what we're looking for mainly. I mean, we could be asked to find these other things, but this is primarily what we're looking for, is the magnetic force acting on a current carrying conductor. So I'm going to erase this now and show you guys the equations for slightly more complicated shapes of wires. And these equations, there isn't a huge difference in these here actually. They're actually quite simple. So what we'll have, as opposed to one big section of wire, when we have a crazy curved wire that's not of any particular shape, it's just like everywhere and crazy, what we'll have, we'll be able to break it into small sections with calculus, doing integration. And I assume you know that. I don't have time in this video to teach it for you, but maybe I can do some calculus in some other videos if anyone would like. But anyways, what we have here is these are actually, I think, called the integrands. We have these small little sections. We're still dealing with current, and we're still multiplying that times B. Our only difference here, like I said, these are small little infinitesimal sections of, say if we have a crazy curvy thing. Well, here's a straight section. There is a IDS. Well, here's the straight section. This is the IDS. Here's another. It's the IDS. Well, if we just keep doing that until we break it into small blocks, we'll eventually have all these little pieces that we can add up. That's essentially what we're doing here. We're using calculus to add up all these small sections so we can know the total current, so we can figure out the total force. So this is our fragment of an equation, and what we get, our equation for if we have fragments. What we'll actually get is an integral, as I mentioned before. If you want to find out the force on some curvy wire, I comes out, it's a constant, it comes outside of the integral. And then you integrate from A to B, that's the length of your wire. That's why L is taken out, because you're integrating from That's why this here is not in this equation, because A to B is essentially your length and times B. So you integrate your individual sections across your magnetic field over this area, A to B, however long your wire is, then times current, and that will give you the force. Okay, without further ado, I'm going to jump into a problem really quickly, see if I can make some progress on that. I'll go ahead and read the problem and get to solving that for you guys. The problem is a wire bent to the